Hey, welcome back to Math with Patrick. It's June 17th, and we're solving problem number 168 from the Daily Epsilon calendar. And let's figure out why the answer is 17 today. This problem actually reminds me a little bit of the April 22nd problem. That one also had a similar setup where we had like a linear equation and then something with a sum of squares. And then in that problem, we had to do a sum of cubes. Although today, it's now a sum of powers of 4. And my strategy for the previous problem was just to find some kind of factored expression for this last kind of sum. And then I could substitute in some of these values into that factored expression. Now, I haven't really come across a factored form of the sum of powers of 4, so I looked it up. There's something really similar. It's called the Sophie Germain identity, and she's like a French mathematician, and she found, or at least there's an identity attributed to her name, where you can factor something like x to the fourth plus 4y to the fourth as some kind of like whole number factoring with more powers and adding and subtracting. I'm going to do something kind of similar where I want to try to find a factoring of, well, y to the fourth plus z to the fourth, though it's not necessarily the Sophie Germain identity, but they're kind of really related. So I think what I'm going to do is actually start out with y squared plus z squared and then square that, because I know that if I square squares, I get powers of 4. So just to kind of expand this, I'll get y squared squared for my first term, so that's y to the fourth. I will get twice these two things multiplied to each other, so I'll get 2y squared z squared. And then my last term is just going to be this times itself, which is z to the fourth. And so if I square this, I will get, well, that. And then maybe if we isolate this part, because that is what we see on the screen here, we're going to get, well, it'll be this minus this middle term. So we can do y squared plus z squared squared, and then minus, and how about let's do 2 times yz squared. There we go. I think if we substitute the z for a root 2z, then kind of multiply some stuff the right way, that's actually the Sophie Germain identity, and so they're like pretty similar. Anyways, now I have a factoring, now I have an expression. Well, it's not technically factored because we have this difference in the middle, but I do have another way to think about the sum of powers of 4. Now, I do have y squared and z squared. That's just the number 5, so I can just really easily substitute in a 5 squared, although I don't have a yz just yet, though I think I have a way to figure out an expression for yz. Here I'll do basically the same thing as I did earlier, but I'll just do y plus z squared, and when you multiply it all out, you're going to get something, oops, that's a plus, something that looks like this. And we know that y squared plus z squared is 5. Actually, you know what? Yeah, why not? I'll do it this way. Y squared plus z squared is just 5. So we'll substitute that and put a 5. And then y plus z is just 1. And so we can just replace that with 1. There we go. So if we do some algebra steps and isolate yz, then we're going to get a number for that. There we go. Looks like 1 squared is just 1. Then you subtract the 5 from both sides. That's going to get us a negative 4. And so ultimately, once we divide both sides by that 2, we're going to get negative 2 is equal to yz. So we can just plug in the negative 2 right here and evaluate what this number is. 5 squared is 25. And then when you multiply the negative 2's all together, we're going to get like negative 2 times negative 2 times negative 2. So that ultimately is just a minus 8. And then 25 minus 8 is 17, and that matches today's date. So there's my solution. I'm all done. Thanks for coming along, and I will see you tomorrow. Bye.